So I think we also could start. Welcome back after the lunch break. And I will directly start with the lecture, which is now on timetabling. And we will first of all see how we can model timetables in public transport. And this will bring us to a very famous model called PESP, or Periodic Event Scheduling Problem, from which we will see some properties and some sketches of algorithms, where I really will show you in practice one nice graph theoretical algorithm how we can compute easy timetables. So we are now in the next step here. We assumed in the beginning that the infrastructure network is already given with stops or stations. And in the last lecture, in the previous lecture, we have discussed how we can find a line concept, including the frequencies. And now we want to find a timetable before we later on continue with vehicle scheduling and other problems. So if we want to model timetable, it is nice to use the event activity network that Alex already has shown you on Monday, where we have for each line several activities. So here we see one line, which is on the top line, that goes from station A over station K to station E. And we have 4 events for this small segment. So each departure and arrival is called an event. So we have a departure at station A, then we have a driving activity to arrive at K-Town, then we have a wait activity that allows passengers to deboard and board, and then we have again a drive activity until we reach station E. And we have other lines that also pass K-Town, so they come from station B or C and they go to other stations later on. So these are drive and wait activities. So far, it would be easy to find a timetable because we only would have single lines and then we just could assign any times that fit. But the lines are connected and they are connected by so-called transfer activities, because it could happen that at K-Town somebody wants to get out of the top line and board another line, so they have a transfer. So if you come from station A and you want to go to station F, then you should transfer at K-Town. And these activities they always start after an arrival and go to a departure at the same station, allow passengers or model or show us that passengers can change. So with black activities, drive and wait activities, they belong to the vehicles, to the trains or to the buses. And with blue activities, they belong to the passengers. And we can also have headway activities that make sure if you are in track-based public transport, that 2 trains cannot depart on the same time if they share a piece of track. So for example, these 2 departures on the top, they go to different stations, E and F, but in the beginning, they might share the same track. And this means that there has to be a security distance between these consecutive departures, and that can be indicated by these red activities that are headway activities. So it's important in this model that if you see an error, such a link, then it's always a temporal link. So that the beginning of this activity has always to be before the end of the activity. So if a vehicle departs at some station, then this happens before it arrives at the next station. And if a passenger leaves a train to board another one, then the leaving of a train, the deboarding has to be before he can board, obviously. And also with the red activities, they present this order in time. So if I have such a red activity, then it makes sure that if this one event takes place, then there has to be some time which we need to accept before we can schedule the next departure. So what we also have are lower and upper bounds on all these activities. So a driving activity between 2 stops or 2 stations usually takes some time if a train goes fast, so that would be the lower bound, and if the train goes slow, we can also have an upper bound. I see a question here. What is headway activity here? headway activity makes sure that we don't have two departures that are too close to each other. So if you have a piece of track for two trains, then there has to be a security distance. So if one train departs, then depending on the signals of a track, it can be shorter or longer. But for example, there could be a security distance of, let's say, 5 minutes or 10 minutes. And such a red activity, which I call headway activity here, would have as lower bound with 5 minutes, making sure that if the first train departs, the next train can follow only after 5 minutes. So these arrows order our activities in time. So this is just to explain or to show that this can all be modeled, also modeled as a graph, but we still want to go back to our old steps. If we now want to formulate the problem as a mathematical program, we have to deal with the variables, the constraints, and the objective function. So, and there are two different ways or two completely different types of timetables. Namely, we can have aperiodic and periodic schedules. And we will start with an aperiodic schedule. So in an aperiodic schedule, we need not respect any order or any repetition. So we can schedule the departures maybe at 9:15, and then the next departure at 10:20, and then a departure maybe at 12:10, something like that. That would be an aperiodic schedule. In a periodic schedule, we would like to have a timetable repeated, for example, every hour. And we will see that this is a bit of difference when modeling and also when solving the problem. And I will start with aperiodic scheduling. So we have our event activity network in the way I have shown it here, where we have all these events. And for the beginning, we can also forget about the headway activities, because if we do it in an aperiodic way, we have to fix the order before we make the schedule. So we have to, they usually come in pairs, and we have to select one of each pair. Otherwise, it would not be feasible. Okay, but that will be clear maybe later. So we have given our event activity network with lower and upper bounds for all the activities. And then we need the variables. And a timetable is defined as something that assigns a time to every event. So the events in our network, they correspond to arrivals and departures of buses or trains at stations. And a timetable is nothing else but an assignment of times to these events. So if you think about the printed timetables, you see all the departure times at every station for every train. That is just giving a time to each of the nodes in our network. And this makes it easy to say that these are exactly the variables we are looking at. We want to determine the time for all of our events in our event activity network. I go back to this network one more time. So you see the nodes here, and these nodes are all arrivals and departures. And if we give a time to each of the nodes, then we would have a timetable. That could then be collected. All departures in K-Town would be the, in Germany, yellow timetable you would find in K-Town at the station where all departures are collected. And collecting all arrivals would reside in the white timetables. Okay, so these are the variables. The second step is feasibility or the constraints. Now the question is, we cannot just give any numbers, but that has to fit together. And to see if a timetable is feasible, that can be done by looking at the lower and upper bounds. Here I have a very small example with only 2 events. Could be a departure event and the next an arrival event. And we have an interval which contains a lower and an upper bound. So if a bus drives from I to J, then it needs for sure 8 minutes. And somebody told us that it should not take longer than 12 minutes. So then we can assign times, and the constraint or the restriction that has to be satisfied is that with 2 times, Pi would be the departure at I and Pj would be arrival at J, that the difference between them namely the time that the trains or the bus spends on the track between I and j should be in the right interval. So this could be checked easily by if we arrive at 9:55, for example, and we depart at 9:45. I just have minutes here, so you can take any hours you like. So then it would be 10 minutes. And 10 minutes is in the interval between the lower bound 8 and the upper bound 12 minutes. So this is fine. But you could not have, for example, chosen 35 and 55, because then the time on this piece between I and j would be 20 minutes, and 20 minutes is not included in the interval between 8 and 12. And in general, the constraint is on the right-hand side of this slide. So we always have, for each activity going from I to j, we have to subtract pj, the end of the activity, minus pi, and this should be in our interval LA UA for all activities A from I to j. Let us check that for a small example. So consider two small, very small networks, and we have lower and upper bounds on the activities. And now the question is, and if we had time and we're sitting together, I would ask you to try it out yourself, to assign times to the nodes such that everything fits. So you can start doing that yourself, but you can also do it together. So we start with example 1. Our first node, for example, we start in the left upper corner and say, okay, we fix this time to 0. We start at minute 0 in this node. We could have fixed any other time or would have chosen any other node to start with, because in the end you could shift the whole schedule. So the first is, we cannot make no mistake when choosing the first time. Everything is okay. So then we have to go to the next thing. And if we now look at this activity here, we see that we have time between 10 and 15 minutes. So for example, we could say we arrive at 10. This is fine, because then 10 minus 0 is 10, and which is in the right interval. And we continue, maybe we say 20 here. We arrive at time 20 on the upper right node, meaning that we take 10 minutes duration on this activity, and 10 minutes is in the middle of the interval between 8 and 12. So this is also fine. And then we continue, we go to this lower left station and we assign a 7. And now it's getting a little bit exciting, because now we have to respect two activities. But if we assign a 15 here, we see that for both activities we have done a good job, because on the one activity we have a duration of 5. 15 minus 10 is 5, which is in the interval from 5 to 6. And on the lower activity we have 15 minus 7, which is 8, which is also in the right interval. So our red numbers here would be a feasible timetable, because these red numbers respect all our constraints. And the constraints are here on the right-hand side of the formula. This is just the type of constraint. Okay, now we come to the other example. The second example is very similar to the first one. The only thing that was changed is that instead of having an interval from 7 to 8 on the two lower activities, on the left activity and the lowest activity, I changed that from 37 to 38. And now the question is, what would a feasible timetable look here? Any idea? Anybody here who sees a feasible timetable? Some cameras are on and people are looking. And if you don't see a feasible timetable, that is not your fault, but it's a fault of this example. In this example, we have no feasible timetable. A feasible timetable for this example does not exist. If you want to have these driving times or these activity durations as indicated, then there's no chance to find a feasible timetable. So if you just invent any network and you invent any lower and upper bounds, it might easily be that you do not end up with something that has a feasible solution. And this is also very important if you start with line planning and you have a line plan, and then you want to find a timetable for the line plan, it can happen that there is no feasible solution, and LinTim will tell you that then. So why can we see that there's no feasible solution? This means that this has something to do with this node here, where a lot of things two activities come together. So you see we have long duration times if we go this path, the lower path. And even if we take the shortest of them, it's 37, we need quite a long time. So like 37 plus 37 is 74. Hopefully is 74. But even if we take the longest here, 15 or 6, we will not at all reach the same time here. So somehow we have to go back to the same node. If we have such a circle where we can take two paths, we see that it should fit together what we do. And here is no chance that it fits together. So there's no possibility to assign red numbers such that all our constraints for the activities are satisfied. We will see later a criterion where we can check that rather easily. And here you can just play around with that. It will not be possible to find a feasible timetable. Okay, so feasibility is important, but we modeled feasibility with this constraint rather well. Now, the last we need is the objective function. And here it is not as it was in line planning, but the objective function is rather easy. Everybody, if you publish or if you try to find timetables, then the idea is, or the goal is to minimize the traveling time of the passengers. Given some buffer times for delay management, maybe later on, but it always deals with the traveling time of the passengers. And most of the papers, of the more conservative papers, want to minimize the traveling time. So we have the traveling time along. So if we could look at the objective function, we sum over all activities. Every activity can be described by a start node or start event and an end event in our set of activities here. And then for each of the activities, we compute its duration by subtracting pj, the time where it ends, minus pi, the time where it starts, and we multiply by the number of passengers using this activity, and then we want to minimize this. And in this setting, the passengers' weights are fixed beforehand. It would be much better if the passenger weights are fixed while we do the timetabling, so including the routing. I will say a little bit about that in the last lecture today. It gets more complicated then. So now we have found a model for the aperiodic timetabling problem. Here is our integer program. Our variables are only with red numbers that we assign to the nodes, which I called pi. They have to respect that the duration of each of the activities. So for all activities A, from I to J, we want to have that the duration of the activity is between the given lower and upper bound. And we want to minimize the travel time, the sum of travel times for all passengers. So that was the aperiodic part. Now we want to find out what we can do if we want to find a periodic timetable. And the periodic timetables are much more important because passengers and people would like to have regular schedules that every hour we have the same time, so it's easy to memorize and easy to run. And if we want to model the periodic timetabling problem, we will end up with a problem called periodic event scheduling problem. But still, that is the name that the problem will get, but we have the 3 steps we usually have to proceed: variables, constraints, objective. Variables. We again look at our event activity network, and in our case, the event activity network now does still have arrival and departure events, but now the event activity network is much smaller because now we need only one arrival and departure event for every line. And we only need to plan for this 1 hour or one period we want to repeat, and not for all the periods. So we have a smaller event activity network and summarize all the arrivals of a line at a station at the same node, because we want to have a regular schedule. These arrivals should take part every 60 minutes. So we need only one node that represents all these arrivals. But everything else is exactly the same. We still have lower and upper bounds, and we have this period. And the event activity network also looks exactly the same as before. It's just a bit another interpretation. In the event activity network, we had for aperiodic scheduling, we had an event for every vehicle, so every bus and every arrival departure at every station. And now we have not for every bus, but for every line, including more than one bus. But still, the periodic timetable is again assigning red numbers to each of our nodes. And in this case, we assume now, for example, if the period is 60, we want to repeat everything after 60 minutes, then it is enough to choose one numbers between 0, 1 up to 59, because then we know if the bus is coming at 20 past, then it will come at 8:20, 9:20, 10:20, and so on. So here we need only to choose values between 0 and the period -1. So still, we can use just this timetable definition as variables. So we have variables, and now these variables are even a bit simpler maybe, so they are still integer numbers, but now we have an upper bound for the variables because we need no assignment which is larger than t-1 because it's repeated every hour anyway. Second step, as before, we have to deal with the constraints. So when is an aperiodic timetable feasible? And here we have again the example similar as before. That was the example we had so far. So we had our activity from I to j, and we had the time window was 8 to 12 was the duration. And we recall that 55 minus 54 was 10, so this is fine. So now we have a periodic schedule, and the question now is what happens if we start here at 55 and here we end at 5 past. If we have a periodic schedule, then this is repeated every hour. So we would have to compare, for example, 8:55 and when the bus drives here and arrives at 9:05. So intuitively, it's very clear to us that still this bus needs only 10 minutes. So from 9:05 going back to 8:55, this is 10 minutes, and this is exactly in this interval. But if we take the same rule as before, we would subtract 5 minus 55, which is minus 50, and minus 50 is not in this interval. So what can we do to close this gap? This is this periodicity, the periodic constraints that you also know in other things that you leave on periodic constraints. You also have in natural sciences and other respects. And the idea is to take it modulo. So what we can do is that we subtract pj minus pi, but when we take modulo the period. So 5 minus 55 would be minus 50, but taking modulo 60 would be 10. And with the 10, we end up in this interval again. And mathematically, this can be done by allowing that we add the period here. So we take the same difference, pj minus pi, as we did on the left-hand side. But then before we check if we are in the right interval, the only difference is that we can add the period t. And since we do not know the numbers before, we do not know how often to add this period t. So in our example, 1t, so minus 50 plus 60, would give us the 10 that we need. But it can also happen that we need to add the period twice or 3 times, or that we even subtract the period, depending on the numbers. So we allow that we can have an integer multiple of a period that is added here. And if and only if this is true, then we end up in this interval here. So if and only if we find such an integer such that we end up in this period, then we are feasible. And this is the same as taking a modulo operation. That sounds a bit abstract, but we can again look at an example. And this is again a similar example as before. So example 3 is in fact the same graph, the same network, the same event activity network as we had in example 2. And recall that it was not feasible if we looked for a aperiodic timetable. Now we consider this again. Here is the thing, and we start with 0 and recall that it was not possible to find red numbers without if the timetable is aperiodic. But now we can do that. So we have a 10 here as before. 10 minus 0 is 10. No modulo is necessary because we don't go over the full hour. 8:80 and 8:10 is no full hour in between. We also can do with 20 as before, no change. And we can do with 37 here. 37 minus 0 is 37, that is also fine. But now we come to this thing here, and we see that if we can take it modulo, everything works out very well, because 15 minus 10 is our 5 here. And here it seems that we go over the full hour. So we start here at 8:37 and end up here at 9:15. And from 9:15 backwards to 8:37, we see that this should be the case. Now I should have written down the period maybe. Good thing. I thought that was fine. Ah, yeah, that should be 38. Right. 15 minus 37 plus 60 is then 38. So this is within our period here. Yeah, if we have 37 and we take a driving time of 38, then we end up here at 15 past. So 8:37 plus 38 minutes is 9:15. So this is fine. And we see that for the periodic case, that works out very well, and we find a feasible solution. Now the question is, if we are allowed with this periodicity, is it then always feasible? And this is not the case. Here again, I changed a little bit backwards. So the only thing I changed is with large intervals from 37, 38 with the large numbers back to 1, 3. And for this example, it can be shown that also no periodic schedule exists. So this also for the periodic event scheduling problem or finding periodic schedules has also not always a feasible solution. Okay, also for a periodic case, we cannot be sure that always a feasible timetable exists. And the objective function is then the same as before. We want to minimize the traveling time. We fix our weights, how many passengers would like to travel along activity A beforehand. And then the traveling time is Pj minus Pi minus the lower bound modulo T. That is now the new way of computing the traveling time. And we want to sum this up. And this would be the classical PESP model as it was defined by Serafini and Ukovic in 1989. They had already timetabling as problem in mind, but it in a more general way, where this T means that we have to talk modulo T. So this is our objective, minimizing the traveling time. And this tells us that all these durations are correct. It looks a bit more complicated, but it is the same as we have seen in the example. But it is not a linear program because modulo is not a nice operation. It's not a plus or minus operation, so we cannot really deal with it. But we can reformulate it as integer linear program by adding a new type of variables. So what we need are new variables. These are the numbers, the variables ZA. So now we have two types of variables, the old ones, which are just the red numbers on our notes, so the times. And we need some auxiliary variables, which are called modulo parameters, and that help us to get the modulo operation in a mathematical good way. And that is just what I've shown you before. If we want to check if the duration for an activity A between Pj and Pi is in the right interval, we can add some integer multiple of the period. And if we are then between LA and UA, then it is fine. And this is then exactly the duration our activity meets, together with this magic number ZA. And exactly this duration is what we also want to minimize in the objective function. So it looks rather easy, this problem. It only has this one type of constraints and two types of variables. And the objective looks even similar to the constraint. But it is one of the hardest problems we know in computer science and optimization. It is called intrinsically hard or whatever. It is even difficult to find a lower bound except of a very trivial one. And also without any objective function, just finding out if there exists a feasible periodic schedule or not is already very hard to do. And this explains here that there's a lot of research work on algorithms for this periodic event scheduling problem. And this is another focus as for line planning. In line planning, we had a lot of different models And this explains why we have so many papers. And for the PESP, we have a very hard problem, which is very hard to solve. So this explains why we have a lot of papers here, and they are often rather mathematically. So this was the main part. I wanted to hope that you understand that we have the possibility to do periodic or non-periodic schedules, timetables, and that this is mathematically a hard problem. I want to show one property of this hard problem, which will help us also to understand the algorithms. And yeah, first of all, I already said that it is a hard problem. But what is very important, and that you already have seen in my examples, are cycles. So cycles are the reason why we are not feasible, because we have to, if two paths go together, we have to synchronize this in some sense. So if we want to find the timetables pi, that are often called node potentials, and the durations are often called tensions, so often they call, the models are called then tension models. When we see if we have a cycle here, the tension, the duration here is 18 minus 10 is 8, 22 minus 18 is 4, or 22 minus 10 is 12. And then what we can do, we can add up the tensions. And we distinguish two types of activities in our cycle. So here we have a cycle. And now, first of all, we have to say in which direction we would like to see the cycle. We can choose that as we like. But for example, here I said the cycle is 1, 2, 3. So we take the cycle in clockwise order. And when we say the activities that have the same order as the cycle, so the red activities in this case are called forward activities, and the activities that go in the other direction, not clockwise but anti-clockwise, are called backwards activities. So we have two forward and one backward activity. Why is this important? It is important because now we can compute the tension of a cycle. And in the tension of a cycle, we add up all the durations of the forward activities, or the tensions, and we subtract the ones of the backward activities. So in our example, we would add 8 plus 4 is 12, and we subtract this one, which is also 12. So we end up with 0. And this is exactly the criterion we need to see if the problem is feasible or not. Because the problem is feasible if and only if we always get 0 here. So adding up the forward tensions and subtracting the backward tension should always be the same. So the forward tension and the backward tension should be the same number, in other words. And this is the tension of the cycle. And then the lemma tells us for the aperiodic case that the tension along all cycles is 0 if we have a feasible timetable, meaning that for every cycle we have that these tensions are 0. And in the periodic case, we have that the tensions along all cycles modulo t are 0. So if our period is 60, then the tension along the cycle, again by adding up the forward tensions and subtracting the backward tensions, is either 0 or 60 or 120 or minus 60. But always if it is a multiple, an integer multiple of the period, then we know that this is always true. So for every cycle, we get that the sum of the tension is an integer multiple of the period. So this was the important property that helps us understanding algorithms. And I want to start with an algorithm for the aperiodic problem. So in the aperiodic problem, we can proceed very easily. And the algorithm is everything we need is here on this slide. So we have an aperiodic problem, and here I have one activity which is grabbed here with a lower bound and an upper bound. So the first step we want to do is to take our event activity network and construct a new event activity network, or the extended event activity network, that we call n prime. And n prime has exactly the same nodes. So all the nodes stay as they are, but we split every activity into two. So we have this activity here, and that is split into two activities, one red belonging to the upper bound and one blue belonging to the lower bound. And it's always the case that we've constructed in this way that the red activity has the same direction as the original one, and as weight, it gets the upper bound. And the blue activity goes in the other direction, so opposite to the original activity, and it gets minus the lower bound as weight. So that looks maybe a bit strange, first of all, but it is very easy to do. You have an event activity network and you just graph the new activities. Then you choose any starting node, no matter which one. And then for all other nodes, you compute a shortest path, which is an easy algorithm for everybody in computer science or traffic planning. So you can use Dijkstra or whatever you like. And the length of the shortest path from S to I gives us the value of the timetable. And this is always feasible. So it's a very easy algorithm which always gives you a feasible timetable. And I think it's quite surprising how easy it is. I want to demonstrate the algorithm at a small example. Also, the proof why it works is not difficult in my lecture. I usually do it, but I skip that here. So here's our given network. The first step is that we want to have this network n prime. The nodes stay all the same. So we still have node I1, I2, I3, I4, but we double each activity. And for each activity, we get a forward and a backward activity. And let's just check here for this one for activity. The forward activity gets the upper bound and the backward activity minus the lower bound. So we get 4 here for the forward activity and a -1 for the backward. And the same has been done for the other things. So we just doubled all the activities and added the right bounds. And then we have to start and find one starting node. For example, we could start with I1, so in the upper left corner. And now we have to find the shortest paths to all other nodes. This can be done automatically, for example, as I said, by using Dijkstra or Floyd-Warshall or Bellman-Ford or any of the good new extensions that you will learn about tomorrow, no matter what you take. And you see the shortest path from I1 to I2, that is 4. And from I1 to I3, we have to add a 2 here, so it's 6. And here too, we get 12. And then 0, 4, 6, and 12 is a feasible timetable. We can check that in the original network that 0, 4, 6, and 12 is a feasible timetable. This is easy, and I want to show you that it would also be the same if we started with I4. So we can start with any node here. And the question now is, we need not get the same timetable, we can get another one. And I just want to show you, if you start with I4, you have to be a bit more careful when computing the shortest paths. For example, the shortest path from I4 to I2, that is not 0 here, but it is better to go via node 3, -3, and then to I2, so you get a -4 here. And also the shortest path to I3 is a -3, and the shortest path to A1 is a -5. So maybe we don't like negative numbers, but we can shift everything. So we could just add 5 to each of the numbers here, and then we have again a nice and clean timetable that we can use. And it is not exactly the same as the timetable we had before, but both are feasible. And so this was the one we had before, which looks not exactly the same. And the theorem now tells us that, in fact, the aperiodic problem is feasible if and only if our new network does not contain a circle of negative length. And in this case, this procedure works, and we get a feasible solution by looking at the shortest paths. Those of you who have studied shortest path problems know that a circle of negative length makes a lot of trouble, because then the problem is not well defined anymore. But this is only the case if and only if our aperiodic problem is not feasible. So either we find out that the problem is not feasible, or it is feasible and we find a feasible timetable. So, and this can now also help us to give a first basic algorithm for the periodic problem, because we could now, for all feasible modulo parameters, fix the modulo parameter set. If we fix these new and nasty modulo parameters, the result is an aperiodic problem which we can use, which we can solve. So we could, for all feasible modulo parameters, solve the aperiodic problem and choose the best solution. And then there's a famous theorem of Odic that tells us that we need not consider all possible values for this set A numbers, but the set A numbers have to respect some equation or some inequalities here that helps us to reduce the set A, the modulo parameters we have to check drastically. Now, that is the first basic algorithm to bring it back, the very hard periodic problem, to bring it back to the aperiodic problem by fixing the modulo parameter and then using the easy solvable aperiodic problem. But there are other ways to do that. One is classical integer programming. I said it's a very hard problem, but still there are techniques with that you can treat problems of moderate size rather okay. And this is by not taking the formulation, the integer programming formulation I have shown you, but by taking a cycle-based formulation, because as we have seen, cycles are the crucial point of periodic event scheduling. So a formulation which is directly based on the cycles is can be shown to be more efficient than other formulations. And then there are also heuristics. Yeah, maybe that is not a good order here. So SAT solving is another way to solve that, also exactly, but by using SAT solvers instead of integer programming solvers. And then there are at least two different heuristics that can be used. One is called the modulo simplex, which is a bit an older one, and one is the matching approach, which is a very, very fast heuristic, and which is also in LinTim, we have implemented all of them here. The matching approach, you will find out, is the fastest one, but it is not very good if you have headways included. So if you only have bus transport where you don't need any headways, then the matching approach works very well. So I have some recommended reading for you here. The basic paper is of Serafini and Ukovic, so that is a little bit more mathematical. So if you are studying mathematics or computer science, I would highly recommend this paper to you because it really has all the basic properties you need to know for the PESP. And then the dissertation of Christian Liebchen in Berlin summarizes very well the state of art at this time and also his own work. If you want to read about the modulo simplex or the fast matching approach, we have papers of our own working group, which I can recommend. And that is what I wanted to tell you about timetabling. And I thank you and pass everything on to Alex again.
At least give you a little bit time to look at the exercises. So I think we will do about half an hour now of looking at the exercise sheet. So again, you find the timetabling exercise sheet in the C file folder. You hopefully know your groups from before, so just go back into your groups and we will have a look again if everything fits together. And yeah, I prepared a few examples, trying out different strategies for timetabling, playing with the weights, integrating passenger routing with Anita, what Anita will tell us later a little bit about. So let's see how far you get and what do you discover. Have fun with it. So thanks for coming back, or otherwise you didn't have much of a choice. So thank you for taking the exercises. So again, I just want to take a few minutes to give you an idea of what I thought about when making the exercise, so that you get an idea for the exercise where you didn't have a chance to work on. We know it's not much time to have half an hour to explore all about timetabling on that we have in LinTim, but at least we hope that you get a first idea and got some idea on how to continue if you want to do so later on. So first of all, the timetabling objectives. Again, I've just put here my values that I got, and we see that the conprop, so the heuristic constraint propagation, is the fastest one, but gets the worst results. A little bit better is match, but it's still quite nearly as fast. And then only a little bit better is the cycle-based IP. So that's the IP based on cycle bases that Anita mentioned in her talk. Yeah, and again, we see a similar image in the perceived time average, but for example, here we see that match finds the better value with respect to the perceived time than the cycle-based formulation, and that's something very interesting that you sometimes see. Of course, CBIP is the optimal solution with regard to TIM objective PTT1, but these two objectives are not the same. So it may be better to run a heuristic when you look for something different than the correct objective function of the optimization problem. Yeah, the plot I should better formulate next time. I think most groups asked me how they should plot that. My idea was you put it in Excel or something similar. And the only thing that I wanted you to see, it's not very nice on toy. We normally do this on larger instances. I just wanted to let it in to get the general idea. On toy, you only see a little bit of correlation here, but more or less the idea is larger TIM objective PTT1 leads to larger TIM perceived time average. And I see that the scale is totally wrong. Something went wrong there. Whatever. Okay. The importance of passenger weights. I don't know how many of you came to this one. So iterating EAN reroute passengers and the timetabling step. So we compute a timetable, reroute the passengers to get new shortest path for the passengers, updating the weights on the activities, and then rerunning the timetabling step. And I think we see something quite nice here. So first of all, in general, it goes in the right direction. So we start with an objective PTT1 of 64,000, and even just one iterations, we go to 50,000. But the most important thing here that I wanted you to see is that it's not clear and that it's not every time going in the right direction, right? So in the end, we end with something that is higher than our value in the second iteration. So this function that we see here is not monotone. And especially in the end, we see here a repeating pattern. So nothing will happen here anymore. So we will not find the optimal solution with regard to the passenger weights when we just iterate it. But we may find a good solution. And that's then what I wanted to show you in the last exercise. The benefit of integration, when we really integrate this stuff, we really find the best solution with regard to TIM objective PTT1 and TIM perceived time average when we integrate these two things, right? We have the integrated formulation with passenger routing inside LinTim. So these are now the normal formulation, so the integer programming model iterated with the rerouting and the integrated formulation solving the integrated problem, which is the hardest one. And yeah, the exercise is for the smallest data set that we have in LinTim. So this last one is really, it's much harder to do and to find a feasible solution. You will not be able to do that in your virtual machines on the larger data sets. But just to show you, even for very small data sets, so I think, I'm not quite sure, but I think I said to you should do it on the data set small, which is 3 stops and 2 edges in between them. And even on such a small example, it's better to integrate it and not do it in an iterative way. Okay, and with that, I come to an end to give you of the idea of the exercises.